Hello and welcome to our introductory session of chemistry, talking specifically about the periodic table and the elements that it contains. This is going to be a first lesson in a multitude of lessons that we're going to be using to teach about this. It's very foundational and very key to build into the rest of the chemical elements as well as the chemical reactions we'll be studying throughout this semester. So first things first, we're going to be learning about the elements. So our first step is we're going to go right down here into the periodic table. So before we start anything, why are we learning this? Well, the standards for this lesson is going to be using the periodic table as a model to predict the relative properties of elements based on the patterns of electrons in the outermost energy level of atoms. What that basically means is we're going to be determining valence electrons, which are the outermost levels of the electron patterns in atoms, as well as how those electrons and how those presentation pieces build up into the overall elements of chemistry, of the elements of the periodic table, the interactions that we observe, the mathematics that we can work, everything built out upon that. And we're going to be using these to look at the form and function of the table, as well as to look for patterns and predictions that are going to lead into future lessons. So the atoms, which is going to be what the periodic table is made out of, are going to be, much like everything else, made of elements. Now these elements each contain a nucleus of protons and neutrons, which are orbited by smaller electrons. So the protons are positive, the neutrons are neutral, and the electrons are negative. So when we look at an atom or an element, the number of protons and the number of electrons are always going to be equal, because we want the atom to be balanced. Now the number of neutrons is going to vary. We're going to talk about that later when we get into a little bit more radiometric information and different types of atoms. Different lesson for a different day though. So reading the elements. So we're going to start here. Very first, we're going to look at, on what you see in front of you, the atomic number. That means the number of protons that the atom has. Like I just said, the number of protons is going to equal the number of electrons. The symbol for what we're looking at here is helium. You can see the name down below. Symbol going to be He. There's a couple other components that are listed here on this particular element for the periodic table that we'll be talking about in later lessons, such as the crystal structure, the electron configuration, and then the details down at the bottom that are going to say noble gas, regular gas. Those are going to be a little more specified as we break out into the different types, periods, groups, families, and components of the elements. Right now, we're just getting the basic foundations. So we're going to worry about the atomic number, the symbol, and we're going to talk about the atomic weight. Now, the atomic weight is going to be the average of every element of helium in the entire universe that's been observed. So that's how you get that 4.003. What ends up coming from the 0.003, because there is an atomic number of 2 protons, it's going to have 2 neutrons in there, which makes 4, but there's a very small amount of helium that's going to have 3 neutrons in there, or even as high as 4. So when you weigh out the average, it comes out to very close to 4, but we have to account for those other different particles. So now we're going to talk about the periodic table in and of itself. So the families, which show the number of valence electrons, which are going to be the outermost level, are going to all have be all in the columns. Each of these families has the same number of electrons in the same valence electron configuration, meaning they're all going to behave in the same way. So we can look at this in form of the periodic table for structure and for patterns, because when we know what the particular element is going to do and how it's going to behave, we can know how it's going to react and how it's going to be predicted in a mathematical equation or a chemical reaction, specifically when it comes to stoichiometry, which we will be talking about later. The periods, which are the rows that go across, are going to show the energy level of the atom. So each period, as you go down, is going to have more and more energy, and conversely more and more mass, because each atom is going to have more protons, more neutrons, and more electrons. It's going to just be bigger, it's going to be denser, it's going to be heavier, more massive as a whole. So those two in conjunction are what we're going to talk about in relation to the form and structure of the periodic table. So How's the periodic table developed and ordered up? So it's going to be broken up into 3 categories. So you can see on the colors here, the metals are going to be in that light blue, the metalloids are going to be in that orange, and the non-metals are going to be in the green. Now, what does that mean? Well, in short, each of these is going to behave in a similar way, meaning that it's going to have the same chemical properties, observational properties, etc., etc., and it's going to have a similar chemical compound overall. That, in conjunction with the rows and the columns that we talked about earlier, is going to make it a little bit more observational. So first of all, metals. Metals will have a metallic luster. They have thermal and electric conductivity, meaning they take electricity and heat really, really well. They're usually hard. They're solid. Exception is mercury, where it is a liquid. They usually can be drawn into a wire, meaning they can be molded. And once they mold into a shape, they will stay in that shape. They have higher melting points. Going back to that, they're mostly solid. They require a lot of energy in order to break down into liquids and even further into gas. They readily lose their electrons, and they have a low ionization energy. The last one got cut off a little bit. So the low electron affinity and low ionization we're going to talk about in a later lesson when we get into more of the properties of the elements as a whole and how they vary among the table. What you need to know for now is they don't readily give up a whole lot of electrons that they don't in way, shape, or form take back. So going to metalloids, these are similar to metals. What I like to talk about is they are semiconductors. They're less conductive than metals. Sometimes they conduct electricity, sometimes they don't. They are more brittle, and they have non-metallic chemical properties in general. So they kind of are a hybrid between metal and non-metal. Think of your computer. A lot of the components in it can conduct electricity, but they can also, as a whole, not conduct electricity if the circuits are broken or if there's a different level of charge added to them. Going into the final category, non-metals. So non-metals are poor conductors of electricity and heat. They're often liquids or gases at room temperature and pressure. They don't really have a whole lot of luster to them. Things like diamonds do have a glow to them, but it's when presented against the light. They don't have a shine in of themselves. They don't reflect, they refract light. We'll get into that when we get more into the carbon structures and organic chemistry. They readily gain electrons, meaning they have a high electron affinity. They will take and give electrons very easily and very readily. Excuse me. All right, so going into bonds, there are 4 kinds of bonds. There's ionic, covalent, metallic, and van der Waals. Now, really quickly, ionic bonds, these are when an electron is given away, such as in the case of sodium and chlorine, to form sodium chloride, which is a table salt. 1 electron in sodium is readily given away to chlorine in order to complete both their rings and make them more stable. However, they are kind of bonded and stuck together in so doing. Then there is covalent. Now, covalent is where you share these electrons, and a lot of times they'll rotate from one to the other as an atom goes. They can be in double or triple molecules. This is how you get gases with that double line there, or nitrogen with the triple line, where they're just all wrapped up together and that they're actually sharing those molecules in order to keep both their rings equivalent. Then there's metallic. So the best way of explaining metallic bonds is like a sea of electrons. What you can see there is the aluminum that's present is releasing its 3 electrons. It is moving into what you call the lattice structure, which is where all the other aluminum is. And all of those electrons are just kind of moving around in conjunction with the positive charged ions, which we will talk about later on in properties. Of the aluminum in order to be bonded near them but not too far from them. This is how you get some components such as iron, which can have a 2 or a 3 charge, and it varies depending on the actual components. And then we're going to talk about van der Waals. These are going to be hydrogen bonds in a sense where there is a slight polarization of the charges and how these charges can pull and attract onto each other. We'll get onto that more when we get into water. And I hope that that was presented as easily for you as we can. We're going to be moving into later sessions for the mole. We're going to be talking atomic properties. We're going to be talking about regular properties of the atoms. And we're going to be talking about, just in general, the new elements of what are being discovered daily. Thank you very much.